All right, senior calculus students, Mr. Lovelace, here we go, chapter 4. So we're going to go ahead and go through a bit of the highlights from this beginning chapter of the integration part of calculus. And I'll highlight a few things and then do a few example problems and then give an overview for the week and talk about Khan Academy and a few other things. So first things first, go ahead and have your book available. And if you would turn to page 45, we're going to go all the way back to the beginning when we first started talking about calculus and the need for it and the two basic problems that calculus tries to answer. So if you look back on page 45, you're going to see what we've spent basically the entire class period once we started introducing calculus concepts, and that is the tangent line problem. And so you'll recall as we went all the way back to the very beginning, one of the things that really sort of spurred interest in this idea was the issue of instantaneous rate of change. So as you can see the difference between the secant line, which gives the average rate of change, which is basically algebra, and the idea of the slope of the line that connects 2 points, we begin to think about, all right, if we were able to extend that concept to find the tangent line at any point along the graph, it's going to tell us the rate of change at the point on the graph where the slope of the tangent line is that instantaneous rate of change. So most of what we did in the first part of calculus was taking a function with a curvature of some sort and being able to identify at any given point on the graph defined by a value of x, we can tell what is the instantaneous rate of change at that particular point on the graph. So that was the tangent line problem. And then back, even all the way back, we talked about on page 46, the second question that really spurs an interest in calculus as a mathematical discipline is the idea of the area problem. So back in geometry, of course, we had all sorts of formulas for how to find areas of regions that were defined by things like rectangular shapes or triangles or even trapezoids. But of course, what do we do if we have a general function which has curvature? We would still be interested in finding the area under that curve defined by the x-axis and the function itself, for example, but we don't really have a formula per se, a geometric formula to be able to figure that out. So even back then, you saw these pictures, sort of we just sort of glanced at them as we went by, but this is a hint of where we're headed with the idea of integration and finding the area under a curve using some basic ideas that we, at least starting with some basic ideas of simple shapes that we can use to try to approximate the area under a curve, but then combining that with the ideas of limits and then even connecting it to what we've been working on with differentiation or derivatives to help us actually identify the exact area underneath a function curve bounded by the x-axis, then extending that idea to other situations. So this is really the problem, the area problem, that is going to be the focus of the remainder of our time in calculus. So that was a sort of a flashback to where we were back in chapter 1. So if you would take your book at this point, go ahead and turn ahead to chapter 4. I apologize for the glare there, but you're going to see a similar thing here at the beginning of chapter 4. This is page 247, where they're showing you once again sort of a generic general function, and then the idea of using rectangular shapes to approximate the area. And what you'll notice here, of course, as you sort of go down the pictures here, that the number of rectangles increases. And then eventually the idea being we're able to somehow extend this idea to the point of just now looking at the shaded region under the graph by taking this idea of rectangular shapes and extending it. And what you're going to see is we're going to be using the limit process to actually find the answer to the question. Okay, so that's the preview. Integration. A couple of concepts in this first section, some definitions, some ideas that we're going to sort of review in this first video and talk about where we're headed, do a few examples, and then let you do some practice before we meet again in class on Thursday. So what's an antiderivative? The definition of an antiderivative, sort of the name tells you, in a certain way, it's the opposite, or it's undoing a derivative. So here's the definition. A function f, capital, you'll notice the connection between the capital F being the antiderivative of the lowercase f. So capital F function is an antiderivative of the lowercase function f on an interval I if the first derivative of capital F, which is the antiderivative, is equal to the original function itself for all the values of x inside that interval. So x is as an element of the domain of the function f, as well as the domain of the antiderivative function. So you're going to see this important connection between the letters, right? The capital letter is the antiderivative, the lowercase letter f is the function. So if we take the derivative of f, capital F that is, we get the original function f. So that's backwards, right? What we did in the first part of this class is we took the original function f and we found the derivative of that. And we noticed we wrote it as f prime. So this is using the same idea of derivatives, but now what we're doing is we're sort of going back a step. We're thinking about the function that we need in order to take the derivative of to get a specific function. So it's a reverse process. Okay, so the main thing here is to note the difference between the capital letter F, the lowercase f, and the relationship between the two when we're talking about derivatives. Okay, now I want to take you over to, on page 249. This section here at the bottom of the page is really important, okay? So there's a couple of things just to highlight here. These words, differential equation. So it's an equation, obviously, because it has an equal sign. Differentials, dy over dx. We've talked about this back in the first part of the course. What does this really mean? What this means is we're finding the function where the derivative of y is equal to the given function f that we're interested in. So what this leads to is this notation. And this notation is really where we're going to live for the second part of the calculus course. This is what we call integral calculus. If you think about the first part of calculus as differential calculus, this is integral calculus, and really connected to those two questions. The original question of the tangent line, what's the instantaneous rate of change? That's differential calculus, so we were looking at derivatives. In this section, we're looking at the area under a curve. This is integral calculus. And when you do the Khan Academy video, when it's talking about accumulation of change in that first video that I've asked you to look at, this is really the idea of accumulation. So we're adding things up. And as Sal Khan points out, this integral symbol, which is really where we live in the second part of the calculus class, kind of looks like the letter S if you sort of stretch it out, use your imagination. And so really this is adding things up. So the idea of this symbol is to add up, to sum up. The sigma symbol, which let me go ahead and write that here so you can kind of see it. And he talks about this right in the video that you're going to watch. The sigma, the Greek letter sigma, means to sum up or to add up. The integral symbol is also an idea of adding things up. So that's a lot of information, which you're really going to make sense a little bit later. But just to get an idea of what the symbolism looks like, this is accumulating area or accumulating change. And the way it happens is we're really going to connect this to the idea of differentiation. So over here, you've got this word anti-differentiation. This is a really great word. You should use it in casual conversation as often as you can, anti-differentiation, or indefinite integration. And we're going to talk about the difference between definite and indefinite a little bit later. So indefinite just means we don't have specific boundaries for this particular function that we're interested in. Okay, but we're going to use this integral sign. This is this word, this sort of elongated letter S. Okay, so what this is saying is that we have an integration happening for a function, and if we do this integration, it actually gives us the antiderivative of the function plus what we call a constant of integration. So this will become important. This will become apparent later why this is important. Okay, so this is really something I'm going to go back to occasionally, every once in a while, just to remind you of the connections. That's on page 249. Okay, page 250, a bunch of rules. Remember derivatives, we had a bunch of rules. What's interesting about this table on page 250 is all the connections. So over here on the left-hand side are our usual differentiation formulas. And really we focused up to here We saw these two occasionally, didn't quite get, I don't think, to these trig forms down here. But if you look at this first set all the way down to here, this is familiar to you. Different derivatives, right? This dx is the derivative of the function with respect to the variable x. Okay, this is the one we used a lot. This is our power rule, x to the power n. Take the derivative, we bring down the exponent, and then we reduce the exponent by 1. So this is one we use an awful lot. Here's our trig formulas. Okay, integration formulas. These are going to be similar. And think about backwards, right? A couple of things I want to point out. The integral of 0 is a constant. And the way we connect this is if you take the derivative of a constant, what do you get? You get 0. Okay, here, the derivative of a constant k is k times x plus this constant of integration. And the way we check it is we go backwards. We take the derivative of this and verify that we get this, k. Well, what's the derivative of k times x? Well, this is x to the 1. So we bring down the 1. You change that to a 0. We get x to the 0, which is the number 1, which just leaves us with k. And then this part, the derivative of this constant, is equal to 0. Okay, this is the one that's really the most important one to think about right now, which is the power rule. So if I have the integral of x to the power n, the result is the antiderivative of this function x to the power n plus this constant. So again, right, if I were to take the derivative of this, how would I do that? I would take n plus 1, that's the exponent, bring that out front, and then reduce this by 1. Well, what's n plus 1 minus 1? It's just n. And remember, I've brought this n plus 1 outside to the front, and it's going to cancel out with what's here in the denominator. So I would just have x to the power n, which is this. And then, again, plus c. c is going to be a constant. The derivative of that is 0. The only thing to watch here is n is not equal to negative 1, because obviously if n equals negative 1, the denominator is 0, and we can't do anything with that. So this is really the most important one on this page right now, which is the power rule. So if we have a function x to the power n, and we want to do the indefinite integral, the way we do it is backwards. So in differentiation, we would bring the derivative out front, subtract 1. Okay, here what we're going to do is we're going to go this way. We're going to add 1 to the exponent and then divide, so that when we take the derivative of this, we get x to the power n. So we'll do an example here of that in a second, but that's the most important rule to look at. Okay, the last thing I want to point out in your note in the book, as you're reading through this, is this process right here on page 251. And we did this kind of back in differentiation. We said if we were going to take the derivative, oftentimes we would rewrite it. For example, if we had a rational power, okay, we would rewrite it. Sorry, if we had a radical expression, we would rewrite it as a rational power, and then we would differentiate it, and then we would simplify. So we're going to do the same thing here in a few situations. We're going to rewrite the original integral, we're going to integrate it, and then we're going to simplify. There's examples here. We'll do a problem just to illustrate that. Okay, quick overview. We'll come back to some of these other topics later as we go through class on Thursday. Just wanted to do a couple of problems. So if you wanted to go ahead and turn, I've asked you over the course of the week to look at problems at the end of this section. So we're going to start with problem number 2 on page 255. And I've written it down here separately on this piece of paper. And it's asking us to verify the statement by showing that the derivative of the right side equals the integrand of the left side. The integrand is this part right here. Okay, so it's asking us to verify that the integrand here is the derivative of this thing on the right-hand side. So if we were going to take x to the 4th plus 1 over x plus c and take the derivative of it, the first thing we would do is rewrite this in terms of a power. So that's x to the 4th plus x to the negative 1 plus c. Okay, and now we want to verify that when we take the derivative of this, we get this. So we're going to write this as dx. Okay, remember this symbol, this means take the derivative with respect to the variable x. That's my variable of differentiation. Okay, so if we do that, we're just going to apply the power rule here, and then we're going to think about this is a constant. We take the derivative of it. What's going to happen there? So the derivative of x to the 4th is 4x to the 3rd. The derivative of this, we're going to bring out the minus 1, and we're going to change that, subtract 1 from the power. And then we have derivative of c, that's just 0. Okay, then we can rewrite this as 4x to the third minus 1 over x squared. Okay, and this matches with the integrand of the integral. Okay, so the connection is the integral of this function is the antiderivative of this function. So the antiderivative of 4x to the third is x to the fourth, because the derivative of this is 4x to the third. The antiderivative of minus 1 over x squared is 1 over x, because the derivative of 1 over x is equal to minus 1 over x squared. And then we always have to throw in this integration constant. And why is that? Well, because in theory, there are lots of functions that could be of this basic form that if we take the derivative of it would give us 4x to the third minus 1 over x squared. Any value of c, as long as it's a constant value, when I take the derivative of that, is going to give me this function inside the parentheses. So c can be anything, any constant value. And so when we take the antiderivative, we just write plus c, understanding this is an entire family of functions. C could be 10, c could be -3, c could be 5 pi, c could be anything as long as it's a constant, and this would give us the same integral, integrand inside our integral. Okay, so that's just example problem number 2. Okay, problem number 8. The directions are: find the general solution of the differential equation and check the result by differentiation. It's a very similar idea. Okay, so what is this asking us to do? It's asking us to find the function where y equals a function of x. Okay, so that when we take the derivative of this function, we get 2x to the minus 3. Okay, so we can think about how to do this just sort of logically, or we can go back to the rules on page 250. Okay, and we can look at our function, which is dy dx is 2x to the minus 3. Okay, and we can think about it in terms of this family of functions, right? This is basically x to a power. So we go over here to our power rule. Okay, this tells us, right, if I take the integral of xn to the of xn dx, it's going to give me x to the n plus 1 over n plus 1 plus this constant of integration, which is always just hanging out. Okay, so if we apply this idea of the integral of x to the power n dx, okay, so here's my function, this is my integrand. So what I would want to do is take this -3 and add 1. So this is opposite of what we do when we take the derivative. And then we're going to divide by the very same thing. So we take this and we divide it here. And so what does that give us? Well, it gives us 2x to the -2 over -3 plus 1 is -2. And then we always have to add this constant of integration. Okay, if we simplify this a little bit further, the 2's cancel, the minus sign remains. We get minus x to the -2 plus c. And this would be our function value f of x, which we would call y equal f of x. So think about now, how would we verify this? Well, this is our using the power rule. That's here on page 250, right here, this one, okay? We could verify this in a similar way we did with problem number 2. So let's check, right? If we take the derivative of x, so this is dy dx, if we're thinking about y as our function of x. Well, how would we do that? We'd bring the -2 out front. We would multiply it times -1. That changes that to a +2. Okay, then we're going to subtract 1 from the exponent, which is -2 minus 1, that's -3. And then we're going to take the derivative of this. This is a constant, that's 0. Okay, so we get dy dx is 2x to the -3, which is where we started. Okay, so once again, we're trying to find the function that gives us this derivative. So we're going to go backwards. That's why this process looks backwards from what we did when we took the derivative. So subtracting 1 from the power, we're going to add 1. And then we have to divide by the same thing. Because when we take the derivative, we bring this out front, we want that to cancel out. Okay, that's problem number 8. Okay, problem 32, going a little further on into the exercises. Okay, it's asking us to, sorry about that. Okay, it's asking us to find the indefinite integral and check the result by differentiation. So we're going to use the process that's on page 251. So if you go back to page 251, you see this process. Take the original integral, we rewrite it, we integrate using a rule, just like in derivatives, we use rules, and then we simplify. Okay, so for this problem, first thing we want to do is rewrite. And as you can see, the way this is written, it invites us to go ahead and multiply that. Okay, so that's the first thing we would do, is go ahead and distribute that. We get this t squared plus 3t cubed dt. Okay, if you look back in the integration rules on page 250, you're going to see one that basically tells us the integral of a sum of functions is just, you can break this apart into 2 like this. Okay, so if we have this sum right here, we can break it up like this. And now we just basically have a power, right? We have a power of t here and a power of t here. So we're going to use that same rule we just did in number 8. We're going to go backwards. So here we're going to, instead of subtracting 1, when we do the derivative, we bring the 2 out front and we subtract. We're going to add. So 2 plus 1 is 3. And we're going to divide by 3. And why do we do that? Because when we do the derivative, remember there's a connection here. We take the derivative, we're going to bring the 3 out front, reduce this to a 2. And we need that 3 to cancel out so that we have the t squared. Okay, plus, here we're going to do the same thing. We're going to raise this up 1 and then divide. So this will be 3t to the 4th over 4. And then we always have this plus c on the end. Okay, so this is our answer. We're going to check it by bringing the derivatives, right? 3t squared over 3. The 3's cancel and give us the t squared. 4 comes out front. The 4's cancel. We get 3t cubed. And then if we go backwards and we factor it out to get this expression, right, this verifies as our antiderivative. Okay, and then lastly, number 56. Okay, this is something called a differential equation with an initial condition. And the initial condition just tells us that 0 is our value of x, and we know the value of the g function when the input is 0. Okay, so we're starting here. We know the derivative of the function g is 6x squared. Our goal is to find what's g. Okay? Well, we know that if we were to use our antiderivatives here, what's the function that gives us a derivative of 6x squared? We know that if we just use that same approach we've just been using, we know the g of x would have to equal, okay, go backwards from derivatives. We're going to add 1 to the power, so make that a 3, and then divide by 3. So it would be 6x to the 3 divided by 3. But then we also have this. Okay, and if we simplify here, we're going to get 2x cubed plus c. Well, it's easy enough to check. If I take this as my function g, and I take the derivative, well, I'm going to bring the 3 out front, change that to a 2. That would be 6x squared, which is this. But I also have this. So there's lots of functions that would satisfy this original equation, right? 2x cubed plus 10, 2x cubed minus 5, 2x cubed plus 0. All of those would have this as its derivative just by applying the power rule and by knowing that the derivative of a constant is 0. So now once I have this family, I'm going to use this initial condition to figure out which exact function I'm talking about, or specifically, what's the value of c? So now I have the g of x is equal to 2x cubed plus c, and I know that g of 0 is -1. So now I just take this information, and I replace the x with a 0 here, and I replace the function value with -1. So I have -1 equals 2 0 to the 3 plus c. Well, what's 2 times 0 to the third power? That's just 0. I get -1 is c. So for this initial condition, c is -1. So that means that g of x is 2x3 minus 1. Okay, so for this function, if I take the derivative, I definitely get 6x squared. And it also satisfies this initial condition. Okay, all right, so there's 4 example problems. Please make sure that you've read carefully through the entire section 1 of chapter 4, and that you do your best at trying to look. Let's take your calendar real quick. Take a look at this. Okay, so here's your calendar. All right, so I've asked you to read through this section carefully. There is one Khan Academy lesson I'd like you to try today or tomorrow. You're watching this video, obviously, and then try these problems 1 through 41 odd. We've done a couple sample problems there. Wednesday, you have office hours available at these hours. Please send me an email if you'd like to meet up. We may try Google Meet individually. We may try Zoom as well. And then there's another lesson to try before Wednesday, and some additional problems. We've just done one from that section, number 56. And then Thursday, this will probably change. It will probably be a Zoom meeting rather than a Google meeting, just because of some technical issues I've been running into. Have those problems done that you've tried, as well as questions about the Khan Academy items. You have a number of Khan Academy lessons. I'm going to move this due date to Friday. Please focus on the ones that have a due date of the 19th or 20th after I change it. Don't worry about the ones that are due next week on the 26th. Okay, please make sure you're sending me emails with questions or using the Google group to post your questions on the parking lot and anything else that's coming up. You guys have a lot on your plate. I know a lot got thrown at you today. So please take it easy on yourself, do your best, but definitely communicate with me and all your other teachers and let me know how it's going so we can make adjustments, all right? Hope you guys are all well and stay safe and healthy, and I'll talk to you again soon. Take care. Bye-bye.